Hi everyone, in today's video we're going to run one experiment using Mip-NeRF 360. We won't be able to finish training in this video because it takes so long time, but once we start training, this means that all the libraries were installed correctly and you can run as many experiments as you want. Mip-NeRF 360 was an improvement over NeRF and Mip-NeRF. So the authors listed three critical issues with the previous methods, NeRF and Mip-NeRF. The first one is parameterization, the second one is efficiency, and the third one is ambiguity. Parameterization is what to feed to the network. And NeRF, they used to feed points. Then in Mip-NeRF, they used to feed Gaussians. And in Mip-NeRF 360, they tried to bound these Gaussians just to avoid having large 3D Euclidean scenes. Another thing is efficiency. As you might know that NeRF trains two networks. The first one is for coarse sampling, and the second one is for fine sampling. And Mip-NeRF 360, they changed the architecture just to make it run faster. Before I start reading this paper, you can better understand this paper if you watch John Barron's video. He did a great job explaining this paper. He's one of the leading authors in this paper. So this video explains Mip 360 paper. I put a link here in this notebook and I'll share this notebook with you guys. So let's first look at how they addressed the parameterization issue. Let us first describe how fully trained Mip-NeRF renders the color of a single ray cast into the scene. So RT equals O plus TD, where O and D are the origin and direction of the ray respectively. And T denote the distance along the ray. In Mip-NeRF, a sorted vector distance T is defined the ray split into intervals. So the split, they cast a ray, they split the ray into intervals. For each interval I, we compute the mean and covariance, the mu and sigma, and the values along the ray are represented by the positional encoding. So they use the positional encoding to encode the mean and covariance for each Gaussian along the ray. But here they address the problem of ray parameterization. Though there exists prior work on parameterization of points for unbounded scene, this does not provide solution for Mip-NeRF context, in which we must parameterize Gaussians. So there are previously solutions in graphics research for points, but here they don't use points, they are using Gaussians. So to do this, we first define a function f of x as a smooth coordinate transformation that maps from r of n to r of n. In our case, n is 3, because they work in a 3D dimensional space. We can compute the linear transformation of a function using this formula here. So f of x is a map. They are mapping the original Gaussians to, they are mapping the original Gaussians. No, let's not use mapping, let's use parameterizing. So they are parameterizing the old Gaussians using a new representation, which is defined in contract. And here they are showing a figure for that. So this is the original camera. The red Gaussians are the Gaussians with the new representation, the contracted Gaussians, and the gray Gaussians are the Gaussians that were not affected, the Gaussians with the old representation. So the blue circle here corresponds with an affected domain, which is this one, contract x equals x, and the yellow circle here equals this formula here. So the point here, they parameterize Gaussians to avoid dealing with large Euclidean scenes. So they want to bound the scene with a distance that within that distance we can safely render the scene without losing much details. So let's say that you want to bound the scene by let's say 10 meters. Other than 10 meters, that you want it to like fade away. You don't want much details from the Gaussians that go beyond that distance. So this is the whole idea, because before Mip-NeRF, this was an overhead. You have to deal with all the Gaussians along the ray. But in Mip-NeRF 360, they parameterize the Gaussians that they don't go indefinitely, they will just bound it in a distance that's safe for rendering. So this is the first issue with parameterization. The second issue with efficiency. Here they are talking about coarse-to-fine online distillation. As discussed, Mip-NeRF uses a coarse-to-fine resampling strategy, figure 3, this figure here, in which the MLP is evaluated once using coarse array intervals and again using fine array intervals, and it's supervised using image reconstruction loss at both levels. We instead train two MLPs, a NeRF MLP, theta NeRF, which behaves similarly to MLPs used by NeRF and Mip-NeRF, and a proposed MLP, theta prop. The proposal MLP predicts volumetric density, which is converted into a proposal weight vector W according to equation 4, but does not predict color. This is the trick. So in NeRF, you train a neural net with coarse sampling, and you optimize that neural net using reconstruction. You train the network, you render the images, and you compute the loss with the ground truth images. Then you resample points for fine sampling, and again using the same pipeline by rendering images and computing the loss for ground truth images. What they are proposing here, which makes the network runs faster, is that they want to get rid of coarse. They're still having coarse sampling, but they want to get rid of computing the loss twice. Because in coarse sampling, you are computing the loss, you are rendering images and computing the loss, but you are not rendering, you are not producing the final rendering. You are just trying to render to compute the loss and resample for fine sampling. So here they are proposing a new loss just to avoid the expensive rendering that takes so long time, and they just predict the density, and from that density they are trying to do fine sampling. Because at the end it is this network that do the rendering. The first network, the sole purpose of the first network is just to improve the sampling. It's trying to find, because you're casting array into the void, and you're trying to find where is the density, where are the volumes. So this is a very elegant change, and which contributes to accelerate the network even faster than before. So this is just skimming through the paper. I'm not going too deep into the paper. I'm also not going too deep into the code, but we're trying to run a single experiment using the code they provided. So the code is written in, so this repository multinerf is actually for 3 papers, Mip-NeRF 360, ref-NeRF, raw-NeRF, and the implementation is written in JAX. So in JAX, we can run JAX on GPU or a TPU, and for the experiments I'm using the TPUs provided by Google TPU Research Cloud. So I have 2 nodes here. One node is just, I'm doing that node for other experiments. So we're doing that on this node, which I created using CUDA resources. I already posted a video about how to set up a TPU machine, and I linked it here in the notebook. So make sure to look at that if you want to set up a TPU machine, or you just want to apply for Google TPU Research Cloud. So let's initiate the virtual machine. Okay, we logged into our TPU virtual machine. So let's get into. There are instructions here to install the requirements, but I have my instructions here because I found these. They are the same thing, but in different order. I found this order more suitable for the TPU virtual machines. So first we have to install conda. We have to install conda, then install JAX or TPU. Then we have to clone the repository and download the datasets, then start training. So let's install conda because it's not installed by default in the virtual machine. Now let's create a conda environment with a Python 3.9, which they recommended here. So let's activate this environment, which we call multinerf. Okay, so I have to restart the terminal session for conda changes to take effect. So I'll do that now. So conda is installed, you can tell by the base here. So let's activate our environment. Now we are into the environment that we will be working on. Now let's install JAX and check how many TPU cores we have on this machine. So to install JAX, copy this command. So it returns 4. Sometimes if there's something wrong with the virtual machine or I didn't install JAX correctly, I got one core and it says that falling back to CPU, I could not access the TPU. So it's a good practice to install JAX and immediately check for that CPU cores. So let's exit the Python shell here. Now let's clone the repository. Let's check if we have it. Yes, we do have it. So let's get inside that folder. nerf ls. And these folders and files should match the ones on GitHub. Internal scripts tests. Internal scripts tests. So the next thing to do is they recommend using running the upgrade command for conda. Then we will install the requirements and open CV for training. It is required by the code, and FFmpeg just to create the final rendering for the videos. So if you finish training, you need FFmpeg just to render those images into a video. So let's install these requirements. For PyCol map, make sure that here they manually install the PyCol map and don't use pip because that's different. So what you want to do is just clone this repository into this directory, and the code is instructed to use that directory internal. So you don't have to install anything. It's just a matter of copying this repository. Just want to open this repository here. So this repository here. So let's put this repository into internal folders. For the dataset, we want to create a directory called nerf data. So let's create that directory inside multinerf. Okay, so nerf data ceiling. Here in this notebook, I put the link for two nerf data, the nerf example data, which is the toy data they usually use to just train nerf or tiny nerf. But the data for MIP-360 is, I get this link by just right-clicking onto this one, copy link address. So it's the first part here. So let's get that data, that zip file, into the folder. It's a 12 gig file. So this data has 1, 2, 3, 4, 5, 6, 7 scenes, and each scene has 1, 2, 3, 4, 5 folders. The images folder is the images in original resolution. Image 2 are the images in the 50% of the original resolution. Image 4 is the 25% of the original resolution. They are reduced by 75%. And image 8 are the 12.5% of the original resolution. So these are reduced by different factors. And the sparse folder here is just the 0. It's the cameras.bin, images.bin, and points3d.bin. These are the colmap output. They contain the camera's positions and the sparse representation, the sparse 3D points. But NeRF does not use the sparse 3D points. They only use the camera's positions. So let's get back to, let's start the training on the stump scene. So a variable called stump and experiments 360. The data directory is the data directory that we just unzip the file in. And this is the checkpoint directory. It will store the checkpoints here. So let's define these variables. Let's start trainings. So when we run the training script, we run into an error says overflow error. Python integer -1 is out of band for uint64. It took me a while just to understand this error. I think I spent a whole day just looking for this error. So it turns out this line of code in the scene manager under pycolmap is throwing this error. But the error message here in the terminal is so confusing. It doesn't tell me anything. It's just there's a problem with this line. But when I took that line and run it into Google Colab, it actually gave me a good error message, and I just understand what's going on. So it says deprecation error. NumPy will stop allowing conversion of out-of-band Python integers to integer array. The conversion for older behavior usually use this line of code. So what is going on here is in pycolmap scene manager, here they are setting the invariant point 3D to the maximum value, to the maximum integer value. And usually in NumPy, you just pass a negative number to an unsigned data type, and this will automatically set it to the maximum number, this number here. So they want the maximum value of an integer of uint64. But the problem is NumPy stopped allowing this conversion in their release notes. So here they're saying attempting conversion from a Python integer to a NumPy value will now always check whether the result can be represented by NumPy. This means the following examples will fail in future and give deprecation error. This is exactly what we're getting in the training script. So I have to change this line here in the scene manager. I have to change it to this line. So let's open scene manager and delete this line and replace it with this one. So we changed that line in the scene manager. Let's see if we can run the training script. I'm in the wrong directory. So now it's training. It finishes 1,400 iteration out of 250,000 iterations, and it saves the checkpoints to this directory here. So once it's finished training, basically you need a checkpoint for rendering, but giving the network more time to train is a good idea. So for the rendering, just use these commands. You have to specify the scene, the experiment, and you have to specify the data directory. Then you just running the rendering script. In the rendering script, you can specify some of the options, but the most important options are the number of frames and number of frames per second. So this is the total number of frames, 50, and this is how many frames per second, how much time that each frame will last. So I use these options. So 50 frames divided by 5, I got 10 seconds video. And you can, if you want to have a smooth video, you can increase the number of frames and just increase the number of frames per second. So mainly these are the three main videos that will be produced by the rendering script: the color video, the accuracy video, and the distance video. So I have examples of these here. So this is the color video. It's a 10 seconds video. So because they have 5 frames per second, you can see that it's not that smooth. So this is the color video, and this is the depth video. They are synchronized in the same way, so you can merge these two videos together just to have the same video as the one they have in their website. But the ones they have in their website, it was because it's so crisp. It gives you an idea that the network was trained for a long time, and another thing is about it is it's so smooth. So they increase the number of frames per second. That's it, guys. This is how to train a Mip-NeRF 360 using multinerf GitHub repository. I hope this video was helpful. Please like and subscribe. By the way, you can find the link to this notebook in the description below. Thanks for watching. Bye.